Hello, everyone.
Good morning, Hassan.
Morning. How are you doing?
Oh, we're doing fine, thanks. Yeah. So.
All right, I think we can get started whenever you're ready.
Yeah, so I guess Dak, you need no introduction. This is the second time you have blessed us with another magnificent project to share. So looking forward to that, please.
Yeah, thanks, Hassan. That is already an introduction. So yeah, so I would like to dive directly into the presentation. So it's about CL Tower in Dubai, and the agenda for today would include the project overviews with all the major structural aspects from the site condition to construction of the foundation and superstructure. I would also touch a little on sustainability before going to the conclusion and open up the Q&A section. So let's start it. So firstly, a few facts. The client is the first group in Dubai, and Noor is the architect, structural engineer, and MEP engineer for the project. The construction of the tower started in May 2019, and the building is expected to complete by the end of September 2023. So it's about 2 years from today. This is the reinforced concrete buildings, and the tower is constructed of reinforced concrete with steel is the secondary material. The reinforced concrete design is done to ACI 318, and steel design and composite design done to AISC 360. And the general contractor for the construction is China Railway Bureau 18, and China State Construction Engineering Corporation is the specialist steel contractor. We have the enabling works done by ZTAS and Dutch Foundation. Those are the two local contractors in Dubai. The site is in Dubai Marina. It is close to the entrance to Palm Jumeirah. It's approximately 20 kilometers from Burj Khalifa in downtown Dubai. So the plot is about 3,600 square meters, and it has a trapezoidal shape. It is between the Kayan Tower by SOM and Al Shufu Road and the vehicular bridge crossing the marina. The tower and the podium are designed to maximize the views to Palm Jumeirah, the Arabian Gulf in the north and north, and the marina in the west. The total built-up area for this building is slightly more than 100,000 square meters. The tower hotel floor have a rounded shape. The floor width and floor depth varies along the height to create a tapering effect. The center core holds elevator and escape stairs. We have the radial showers in between the hotel rooms. While most of the super tall buildings are mixed use, this is a hotel building. So there's no office, no residential apartment, it's just hotel and amenities. The typical floor to floor height is 3.5 meters, and there are 1,042 keys in this hotel. On the south side, there are 12 garden terraces and 12 AGR between the terraces. All of them are facing the Palm Jumeirah. If you see if you see this is the location of the garden terraces and atrium, and then we have the width and the depth of these atrium vary also along the height. And then, the design team for the interior is based on wabi-sabi. It is a Japanese philosophy. that promotes the beauty of imperfection, impermanence, and simplicity. From the base, we have basement, ground floor, which hosts the front of house, back of house, and MVP area. And then we have the main entrance on level 1. The podium is between level 3 to level 11. Level 3 to level 9 are the parking floors. Level 10 is the main kitchen, and level 11 is the leisure deck with infinity pools and landscape. So there are 3 MVP floors along the height of the tower. They are at level 21, 54, and 73. Level 76 includes horizon bar and infinity pool, while level 81 is an observation platform. So the tower is 366.5 meters above the ground. The building is under construction. The tower core is currently at level 33, and the top slab at level 30, which is 125 meters above the ground. And this is the current structure from An Su Phu Road. It is about a third of the final height. This is how the tower would look like when it is completed. Because the road curves before leading to the vehicular bridge, so the tower would appear in front of your windshield when you ride to Dubai Marina. About the site condition and design challenge, firstly, I would like to preview about a few milestones. So on the 10th April 2018, NOR started working on the concept design. Prior to this date, the client had been developing a tall residential building on the same plot, for which the contractor had completed the shoring, excavation, and piling works. On the 31st August 2017, but due to the market correction, this proposal that they call Project X, this Project X, it was cancelled, and all the site activity was suspended. And then NOR was then approached by the client to design a super tall hotel tower, utilizing the existing board piles. We have been continuously working on the job for a year, and on the 27th May 2019, the construction restarted again. And we obtained the piling permit on the 1st October 2019, and the full structure permit on 22nd January 2020. On the 2nd November 2020, we also obtained the building permit for architecture and MEP. This is a photo of the site taken in 2018 during our first field visit. So the site was fully excavated, and the existing shoring system already in place. It's a diaphragm wall system with the compression stress in between the diaphragm walls. All the bore piles, including testing by head breaking, have all been completed. This is the foundation of the Project X. So the structure system includes 2 rectangular core here, and mega columns on a 3-meter thick rough foundation, and the tower layouts and also the pile layouts are in north direction. This is a 3D view of Project X foundation, and this is the cell tower that NOR designs. It had a center core, 11 radial shielders, and 2 columns. The structure arrangement is in north-south direction, with it basically this direction. The challenge is for this job is how to design a super tall tower, which is significantly taller than Project X, but utilizing the existing bore piles and complying to the site condition and constraint. So we face a few troubles at the beginning. Firstly, the cell tower is about 60 meters taller than the Project X, so there would be higher gravity and larger loads at foundation. The new tower configuration, which is the cell tower, makes existing pile highly unfavorable. Many piles cannot be fully utilized because they are away from the center of the tower. Thirdly, in case we need to add new pies, we are left with limited space between the setting piles. And finally, due to some complications that are associated with the excavation and shoring works, the local authority request the developer not to do any deeper excavation for the new building. So we look into a few solutions. Firstly, we reduce gravity load. We investigate various primary materials, various column grids, and floor framing system. Plus, we propose lightweight architectural components. And secondly, it's about the lateral force. In order to minimize lateral force, for wind, we run the workshop on form finding and shape optimization with our design architect. For earthquake, we perform a probability seismic hazard analysis to assess the real seismic activity of the site. For the new pie, we also employ full 3D geotechnical modeling of the foundation. Besides assessing the pie load and settlement, it helps us to assess the pie geotechnical capacity, especially when the pie spacing is less than 2.5 times the diameter. So finally, for form finding and shape optimization, the purpose is just to minimize the windfall acting on the structure through the envelope. And we investigate 5 architectural shapes for the towers under wind load in northwest direction. So the first 4 shapes from shape 1 to shape 4A, and they are 320 meters. Shape 4B is 20 meters taller at 340 meters. So in all 5 different shapes, the configuration of the podium are the same, is the same, and the total floor build-up area is also the same in all the shapes. So the 50-year wind speed for the CFD analysis is 45 meters per second. And we've used a typical gradient wind profile for this CFD analysis. No dynamic property, no surrounding structure have been considered in this study. So this is the result for shape 1 rectangular prism. We could see a very large wake region behind the tower. And this is the result for shape 2 with a square prism. And this is the result for shape 3. It's a rotated prism. And this is the result for shape 4A. It's a taper cylinder. So this shape has a minimum wake region and least turbulence behind the tower. And this is the last one, shape 4B. It's a taper cylinder plus the crown, and there's an opening in the crown. So this shape is 20 meters taller than the other shape. Again, we found small wake region and less turbulence behind the tower. Let's watch a short animation about the wind path line around shape 4B. Yeah, so then when we compare the results, we put the base shear and base moment of all 5 different shapes in this table. And if we assume the base shear and base moment for shape 1 at 100%, then shape 4A is the most efficient shape. Both the base shear and the base moment are about 50% of shape 1. But the shape 4B is also efficient because the base shear and base moment are about 60% of the ones in shape 1. So this shape is selected for further development. And here's the final configuration of the building. The tower is 366.5 meters above the ground, with 5 major design elements: basement, ground floor, podium, the tower, and the crown. This is a view from Palm Jumeirah. The night view. Moving to structural system development, at the base, we have ground floor, basement, and foundation, of course. The podium includes level 11 to level 1 to level 11. And then the tower, and finally, we have the crown from level 7-6 to top of the building. On the south side, we have those are the 12 different garden terraces and the 12 arches between the garden terraces. At the mechanical floors, we have the outriggers and bellwether system. They are at level between level 21, 22, level 53, 54, and level 73, 74. So in the structural system for this building, in a short sentence, is building wall system enhanced by reinforced concrete outriggers. So during the concept design, we investigate different primary material, structural risks, and floor framing systems. We also work with the QS for an initial cost plan. We later drew out the steel and composite design because of high costs and selected the reinforced concrete as primary materials. So the tower core holds again the elevators, escape stairs, and MEP services. There are 11 radial showers and 2 L-shaped columns on the sides of the atria. Those are the L-shaped column. So on the framing plan, the typical floor includes 200-meter thick reinforced concrete slab inside the core and at the corridor. The remaining area of the slab is 240 mm thick post tension. The post tension slab is optimized to reduce its cell weight while still meet the deflection criteria and has a reasonable reinforcement ratio of 75 kilogram per cubic meter. On the south side, we have the horizontal steel truss with vertical cables to support the atrium facade, and then we have vertical steel frames to support the panoramic elevators, which run 300 meters from level 1 to level 75. We introduce a combination of lightweight partitions and lightweight floor screed in the typical floor. So basically we use drywall with a density of 400 kilogram per cubic meter, and then lightweight masonry block with a density between 1100 and 1300 kilogram per cubic meter. We also use the lightweight floor screed with a density of 1800 kilogram per cubic meter. So on the typical floor, we have a superimposed desk load of about 4 kilonewton per square meter. This is also the minimum requirement for residential building by the local authority in Dubai. Alternately, we also study a voided flat plate system with plastic void former in the middle of the concrete slab. So this system provides 10% reduction in cell weight of the floor slab, but which is equivalent to a 2.5% reduction in the total cell weight at foundation level. However, this system, it has a few disadvantages. Firstly, we have limited supplier in the local market and also limited number of the contractors who are familiar with the system. Secondly, this is basically an RC slab, so the system requires more conventional reinforcement steel. It could be up to 180 kilogram per cubic meter. So it is actually slightly more expensive than the PT slab for long span. And thirdly, the system requires a slightly longer slab construction cycle than the potential slab, because in order to avoid floating of the plastic balls, then you need to do the concreting in 2 stages. And then also the installation of the conventional reinforcement is more laborious. So we abandoned this alternative, and this is a typical hotel floor with a garden terrace between the the atrium facade, and the panoramic elevators. This is level 21, which is an MVP floor. So we have 8 deep reinforced concrete outrigger beams between the radial shear walls and the center core. This is level 21 framing plan. So you can see this is the outrigger beam, four outrigger beam on the south side and 4 outrigger beam on the north side. Because the perimeter core wall is relatively thin compared to the size of the outrigger, so we provide some reinforced concrete beam running the edge of the core to ensure good connectivity between the outriggers and the perimeter core walls. So when we combine level 21, which is an MVP floor, and level 22, which is the residential floor directly above the MVP floor, we have a complete system of the outriggers and bellwork. So the 2 slabs over here are 300 mm thick, and they are reinforced concrete slab. And we have 16 outrigger beams, 8 beams on level 21 and 8 beams on level 22. So the beams are between 1.5 meter and 2.2 meter deep. And at the perimeter to connect the 2 slabs, there is 750 thick reinforced concrete bellwork. Of course, we provide large opening on the core wall, on the bellwork for ventilation. This is a 3D view of the tower crown, and the center hole is called the eye of the needle. It is a design feature, but also has to reduce wind force acting on the top of the tower. So the crown is a 60 meter tall. It's from level 76 to top of the building. It has 2 reinforced concrete cores and steel movement frames at the perimeter to support curtain walls. And the frames are upraised to the RC core at every 10.5 meter. So level 76, there is a horizon bar and infinity pool. If you see the steel post placed on top of a perimeter beam, which is spanning between the shear walls. This is a view from the infinity pool on level 76 to Palm Jumeirah. You could see far away, that is the Atlantis, the Palm, which is also a NOR project between 2005 and 2010. This is level 81, which is the observation platform. So the floor structure comprises a 200 thick meter deck concrete slab on top of steel beams that span the 2 RC cores. If you can see on the north side, this is north side, south side, there are 2 steel trusses that support the planted column. The trusses are spanning between the between the corner steel columns. This is the framing plan of level 81, and you could see that the curved truss here on the north side and another one on the south side, they are basically placed back to the core horizontally. This is level R1 is the top of the building. There is a BMU machine for maintenance. This is a rendering of the podium structure. So it is a design intent that to float the podium structure above level 1 through a series of V-shaped columns to create an impressive and spacious drop-off entrance to the hotel. So we're going down from top of the podium. This is level 11. It's a leisure deck with infinity pools and landscape. It's a 3D view from infinity pool on level 11 toward Palm Jumeirah. This is a typical parking floor. So the framing plan of a parking floor includes a 5 meter long cantilever slab on the left side here. This slab is supported by post-tension band beams going out from the shearers. The floor-to-floor height of a parking floor is 2.9 meters, and the beams are 600 millimeter deep. So the clearance underneath the beam is exactly 2.3 meters, which meets the minimum design requirement. And there are 4 planted columns that are circled in red. They sit on transfer beams at level 3 and level 4. These columns support 8 floors. So on the right, we have a 300 mm thick post-tension slab, and the slab is sloping around Iceland at about 5 to 7%. This connecting to the upper floor. This is level 3. This is the first parking floor, and you can see this is the transfer structure. So we have 1 transfer structure here, 2, 3, and 4. So the most critical transfer structure is at this corner. It basically, this is an elevation of that transfer structure. We have 10.5 meter cantilever beam supporting planted column, and this column again supports 8 floors above. To control the deflection, we put in a diagonal steel member. And on this side of the podium, each pair of reinforced concrete column is supported on a V-shaped column underneath, which is between level 1 and level 3. This is 3D view of level 1. You can see the V-shaped columns, and on the left side and on the right side, there's a terrace. There's an outdoor terrace here, which is column 3. It is just beneath the transfer structures on level 3. And there's a ramp from ground floor to level 1, and there's another ramp from level 1 to level 3. Ground floor, it basically hosts the front of house, back of house, and parking and MEP areas. The reinforced concrete slab is 350 mm thick. And this is the basement. It's fully dedicated to MEP services and water tanks. We have a retaining wall running at the perimeter. These are the 3 structure models that we use in design. We use ETAFs for checking global stability and reinforced concrete design. We use SAP 2000 model for steel design, and finally, at the when we got to the very end of the design, we built a Midas chain model for validating the global stability and design of critical elements. We found the results are consistent among 3 software packages. These are the first 3 most shapes. Most 1 is a translation of mode with a period of 10.4 seconds. Mode 2 is another translation of mode with a period of 9.2 seconds, and mode 3 is a torsional mode. The period is 3.5 seconds. Yes, mode 4, mode 5, and mode 6. So the first 6 modes account for 60% of mass participation in this building. But in design, we consider totally 36 modes, which account for 99% of mass participation. This is a 3D model of a tower crown. Moving to wind and earthquake engineering. As you may be aware of, the design of tall building in Dubai prior to February 2021 is regulated by Dubai Municipality Circular 191, which sets the parameters for wind and earthquake design to ASCE 705 and UBC 97. So the 50-year basic design wind speed is set at 45 meters per second. These charts are from a local wind climate study. According to this study, the predicted 50-year wind speed for Dubai is 38 meters per second. So if we use 45 meters per second, it means a return period of about 400 years. it is quite conservative. So, but that is the local regulation. So the wind is using 45 meters per second in design. In the wind tunnel, we tested two configurations of the surrounding. The photos on the left show the existing shrouding, and the photo on the right show the future shrouding in Dubai Marina. Just a comparison of wind base shear and base moment from wind tunnel test, the cost pay calculation, and the CFD analysis. So the result from the wind tunnel test is least conservative in this case, and it has been adopted in design. For serviceability, we consider a damping ratio of 1.5%, and maximum the inter-story rip is less than H/400 or 0.25%, and the lateral displacement at the top of the tower is also less than H/500 or 700 millimeters. For acceleration, we investigated the tower structure under two different damping ratios, 1% and 1.5%. So the acceleration and torsional velocity in both scenarios are well below the allowable limits for residential buildings. We don't need a supplementary damping system for this tower. So earthquake engineering is, again, we use the seismic provision in GBC 97, which is the inelastic force deformation curve that is on the slide. To determine soil profile, we conducted also cross-hole seismic test during geotechnical investigation, and the average shear wave velocity for the first 30 meters beneath the foundation is 940 meters per second, which indicates a soil profile SP. Just a bit about the regional tectonic plates. So the Arabian plate is moving north at a speed of 2 to 3 centimeters per year, and it collides with the Eurasian plate and in India plate, and creates the Jagd thrust flow belt and Makran thrust, which are the two major sources of earthquake in this region. However, if you look into the historical seismic activities in the 1900s, which is on the right image, you can see that Dubai actually in a low seismic zone. Then we actually obtained the response spectra from the probabilistic seismic hazard study. If you notice that the desired earthquake, which is having the same period of 475 years as the one in GBC 97. So in this graph, we plot the desired earthquake, which is in green, against the response spectra of zone 1, zone 2A, and zone 2B in GBC 97. And we found that the actual, by looking into this, we found that the actual seismicity of Dubai is very close to zone 1. So the regulation says designed for zone 2B, which is conservative. So with 5% damping ratio, maximum inter-story rip under seismic load cases are also less than the allowable limit of 2%. And this is a comparison of base shear and base moment from earthquake and wind to reflect the load factor from combination wind force and moment multiplied by a factor of 1.6. So you see that this graph, so that for the superstructure design, the design of elements is governed by wind. This is the wind base moment. However, at the height of around 270 meters and above, the seismic moment is slightly larger than the wind moment, and the desired field members is dominated by seismic load. This is called the higher mode effect, because the higher modes with short periods corresponding to a large spectral acceleration. Moving to foundation design and construction, this building is founded on pipe foundations, of course. Pipes take 100% of the load. Soil bearing capacity underneath the raft is ignored, complying to Dubai municipalities regulation. So to support the CL tower, we have put in additional 22 pies. So 21 of them, 1.5 meter diameter, and pie length is 48 meter. They have a compression capacity of 37,000 kilonewton, and we also put in 1 meter diameter pie with a compression capacity of 11,000 kilonewton, with a length of 29 meter. So there are totally 175 pies in this building. This is a 3D view of the foundation. So under the tower, we have 122 pies. All of them are 1.5 meter diameter. And in the podium, we have 47 pies. 20 pies are 1.5 meter in diameter, and 27 pies are 1 meter in diameter. The tower raft is 4 meter thick, where the raft is folded to accommodate the elevator pits. The thickened zone is between 7 and 8.7 meters. In the podium, raft thickness varies from 1.6 to 2 meter. And it's locally thickened to 3 meter and a few columns. The retaining wall around the perimeter is 400 mm thick, and this is the cross section of the raft. So the tower raft is folded, and we have this is the pit for the passenger elevators, and this is the pit for the service elevator. So the cross section is quite complicated. To analyze the raft on a large group of pie, we perform soil structure interaction study. We did several interaction. This is between the structure engineer and the geotechnical engineer in order to arrive with a set of pie stiffnesses. The purpose of this exercise is to determine pie spring constants for a large group of pies, and also for estimation of foundation settlement. Here is the structure model with pies and raft with various thicknesses. So we model the foundation in both SEP and ETAS model. See the geotechnical model in plastic 2D foundation. The geotechnical engineer models raft, pies, soil and rock layers, and reaction from the superstructure are provided by us, with the structural engineers. This is a geotechnical section. So we have 3 soil layers underneath the raft foundation. The first layer is medium dense and dense silicon with SPD number between 11 and 49. The second layer includes very dense fine to medium sand with gravel. SPD number is slightly more than 50. And the third layer is consisting of extremely weak and weak to hard cancaronite sandstone, conglomerate, and siltstone. They are all interbedded. Rock quality definition varies from 0 to 100%, and unconfined compressive strength varies from 0.1 to 17.9 MPa. The estimated foundation settlement is about 50 millimeters, with maximum differential settlement of 20 millimeters, and angle of rotation less than 1/1000, which is all good. We also monitor the foundation settlement during construction. We put in five monitoring points under the tower raft foundation, and 2 points under the podium. The measurement is reported to us on a monthly basis for a period of 36 months. This photo shows the temporary works for construction of the new pile. So firstly, the contractor had to protect the projecting debris from the existing piles, and then partially backfill the site to create a piling platform, and then they build a temporary ramp down to the piling platform from this service road, and then carrying down the piling from temporary platform, and finally they have to remove the backfill again. We use high performance concrete for the foundation. So the concrete cylinder strength for the tower raft is 60 MPa, and for the podium raft is 50 MPa. We've been using triple blend concrete mixes, which consists of 50 to 55% GGBS and 5 to 7% micro silica. We also maintain a very low water to cement ratio. You could see on the slide, and a very high slump up to 700 millimeters. So the main advantages of using high performance concrete is that we were able to save casting time and labor cost. We also can maintain a consistent concrete quality and uniformity, especially in areas with high rebar congestions. And lastly, we able to reduce the vibration and noise, especially for concreting at night. So the foundation is constructed in 3 stages. So pour 1 is the green zone. It is basically the lower part of the tower raft, and then pour 2 is the tower raft plus the podium raft on the left side of this pour strip, and pour 3 is the podium raft, remaining area of the podium raft on the right side of the pour strip. And this was a short video with information about pour 1. So for pour 1, the contractor put in 2,500 cubic meter of concrete, and in 210 trucks. It takes 14 hours to complete. This is the photo of NOR design team during a field visit to witness pour 1. So pour 2 was done in the 8th of August 2020. It includes 7,000 cubic meter of concrete in 580 trucks. It takes 48 hours to complete the pour. It is the largest pour that we have done for a single raft. In the Red Sky view, we did the larger pour of 11,000 cubic meters, but that is for 2 separate tower rafts. So pour 3 were done on the 38th August 2020. We put in 1,300 cubic meters of concrete in 110 trucks. It takes 14 hours to complete. So the total volume of concrete for the foundation is 10,800 cubic meters. The total tonnage of rebars is 3,300 tons. So the reinforcement ratio is about 300 kilogram per cubic meters concrete, including starter bars. We also monitor the heat in concrete during aeration, because when the internal concrete temperature is too high, there's an increased potential for delay actinide formation, which is material related issues that can lead to severe cracking. So to avoid this, typically we keep the maximum internal temperature in concrete at 80 degrees Celsius. So even the raft is 4 meters thick, the maximum recorded temperature is around 75 degrees Celsius. For superstructure design construction, this project, again, it's the reinforced concrete design done to ACI, and steel and composite design done to AISC 360 2010. For vertical elements, the concrete cylinder strength is 70 MPa for the first 100 meters, and 60 MPa for the next 120 meters, and 50 MPa for the top part of the tower. For beams and slabs, concrete cylinder strength is 40 MPa throughout the building. We've been using rebar upgrade 500B for ductility and detailing. We comply to the provisions for ordinary reinforced concrete wall and intermediate moment frame. We also use high performance concrete for superstructure. Again, we use triple blend mixes with 26% GGBS and 5 to 9% microsilica for verticals. At the same time, maintaining low water to cement ratio. But we request for a very high slump up to 700 millimeter for pumping. These are typical mixes that we've been using for most of our tall buildings in the UAE. We did also long-term vertical shortening analysis for the tower in compliance to ACI 209. So the graph that we see on the right here are for half of the pawns on the typical floor plan. The maximum expected shortening is about 80 millimeters, where it's happened at pawn number 13 with a small column beside the atrium. Pawn 1 has also a maximum shortening of 75 millimeters. So in general, we provide compensation or you get super elevation of 5 millimeter at every 5 floors. And we did it for level 15 to level 75. This is the long-term horizontal displacements. So because the displacement in that direction, as you can see, is not critical. It's about like 5 millimeter in 30 years, so it can be neglected. But the horizontal displacement in y direction, basically because the tower is not symmetrical. We have a 300 meter tall atrium on the south side, so under the gravity load, the tower would tend to move to the south. So the maximum lateral movement that we expect is around 40 millimeters, and it's happening around, I would say here is maybe 260 millimeter above the ground. So this lateral movement in north-south direction will be compensated by adjusting the jump form to provide horizontal cambering at those floors. We also monitor the strain and vertical shortening in concrete walls and columns using strain gauges in combination with optical survey method. So we put in the Geocon model 4200 strain gauges at various points on the floor. We monitor strain and then calculate the vertical shortening for a period of 36 months. As I have mentioned, there are 12 garden terraces along the height of the tower, and in between them we have 12 atria. So this is a typical atrium between two garden terraces, one at level 68 and the other one at level 74. So this atrium is about 27.5 meters tall. It is on the, this is the plan of the atrium. So the garden terraces between the panoramic elevators and the curtain wall in front of the atrium. This atrium is naturally ventilated through cedar louvers on two sides. Now the The structure system that supports atrium facade, it includes a series of horizontal steel trusses that are spanning between the two L-shaped columns. These trusses resist the larger wind force. And then we have also vertical cables that take gravity load from the glass panels to the steel truss, and then finally transfer the gravity load to the curb reinforced concrete beams at the garden levels. The front cables, this is a structure model of the system. So the front cables are 16 mm diameter, and we have a cable at every joint to support the heavy gravity load. The back cable 12 mm diameter, and we have a cable at every alternate joint, mainly to stabilize the bottom chord of the steel trusses. So this system, it is designed in an isolated model similar to the one that you see on the left side, so when we design the trusses and the cable in this model, we have busy pin connection at the end of the trusses, and we model the cable at a tension only element. We also check the system for extra compression loads from the tower superstructure, because during an extreme wind and seismic event, the tower may be rotating and then maybe imposing more compression or tension load into the steel trusses. So we also model the trusses in the complete 3D model to check this effect. The final demand and capacity ratio of steel members are basically a combination of the ones in the isolated models and the D/C ratio from the complete 3D models. This is a typical V-shaped column between level 1 and level 3. Of course, this is truss action. So we have the diagonal columns to resist axial compression force, and the connecting beam between the two diagonal columns supporting the resists the tension force. And we've been designing that column. We've been designing that beam using a composite section. So we use an I section embedded in concrete to take 100% of the tension force and also 100% of the shear force in the beam. This is a photo of the V-shaped column. The vertical rebars are being installed. This is the construction of 10.5 meter cantilever structure at level 3. So this is the planted column, and this column is supporting 8th floor. The length of this beam is 10.5 meters, and this beam, even though it had a very big size of 3.5 meter by 2.8 meter, we still need this diagonal member to control the reflection. So to avoid locking stress in the steel diagonal member, we did the full welding at one end, and the welding at the top end was done after completion of level 15 floor slab. Then after that, after we do the full welding for the diagonal member, we can remove the temporary props underneath the beam. So the last session is about sustainable engineering. So I would like to state a few facts. Probably you may be well aware of those after Hassan's presentation. So firstly, the building industry produces 50% of global greenhouse gas emission. Second, the structure of a building accounts for about 50% of its embodied carbon. And the third one is it is estimated that our profession is responsible for around 10% of all energy-related carbon emission worldwide. So therefore, I believe structural engineers are essential players in the fight towards sustainability. So the Carbon Leadership Forum also launched the Structural Engineers 2050 Challenge, which inspires engineers to work toward embodied carbon benchmarks while contributing essential data along the way. So this is the life cycle of a building from module A1 to module C4. So there are three processes that contribute greatly to total emissions. The first process is the product stage, which is module A1 to A3. It accounts for around 50% of emission. And then we have the uses, which is modules B1 to B5, accounts for 20% of the emission. And lastly, operation, module B6 to B7, it accounts for about 23% emission. So in the rest of the box, you see that is from module A1 to A5, this is called Cradle to practical completion. And those modules account for 55% of total emission. This is the playground for structural engineers and architects, because MEP engineers are mainly involving in the third process with the operation, module B6 and B7. So we run a calculation for structural embodied carbon for module A1 to A5. We gather carbon factors of concrete mixes, rebar, post-tension strands, structural steel, and various environmental production declaration that we got from manufacturers and suppliers in the UAE. We then estimate the material quantities from the structure model, Revit model, and also from the BOQ. The calculation for embodied carbon and the carbon footprint is very straightforward. The embodied carbon equals the material quantity multiplied with the carbon factor, and you have the carbon footprint equals the embodied carbon divided by the build-up area. So for this CL tower, the structure embodied carbon is 98,260 tons, or approximately 100 kiloton CO2 emission. We have a built-up area of 101,000 square meter. So the carbon footprint is 965 kilograms CO2 emission per square meter. And those are the carbon footprint in different structural components. 77% of carbon footprint is found in superstructure, 12% in foundation, 8% in piles, 2% in substructure, and also 2% in the temporary work. So this distribution reflects the configuration of this super tall building. You may have asked how large is the carbon footprint of 965 kilograms CO2 emission per square meter. Yeah, sorry, some technical issue. So I'm giving two numbers over here. One number is the return fly from London to New York, has a carbon footprint of 1,000 kilograms CO2 per economy class passenger. And the other number is that for a simple and standard buildings, the structure embodied carbon is somewhere between 200 and 600 kilograms CO2 per square meter. So the CL tower in 965, it's a super tall building. What I would say, if you take the total built-up area of more than 100,000 square meter, it's CL tower, and if you spread it horizontally in a 3-story reinforced concrete structure with a 9 by 9 meter column grids, the carbon footprint could be well between the 200 and 600 kilograms CO2 per square meter. But CL tower is a super tall building. So the question is how to benchmark the design of CL tower to the tall buildings that are sitting or recently completed, and to see whether our design is aligned with the industry practice. Let's look into some carbon footprint benchmarking data for buildings by David Collins in the Structural Engineers, published in the issue of November-December 2020. So you see on the graph, this is the structural embodied carbon in kiloton CO2 emission, and the building type per the area of the built-up area. You see that this is CL Tower. We have a built-up area of around 100,000 square meter, and the embodied carbon is about 100 kiloton CO2 emission. It appears there's a linear relationship between the embodied carbon and floor built-up areas. This graph shows the relationship between structural embodied carbon, number of stories, and the building types. And this is, again, this is CL Tower, but based on the data that we have in this chart, there doesn't, I mean, it does show a clear relationship between the two parameters, the embodied carbon and the number of story. This is the third graph, which shows the building embodied carbon footprint in ton of CO2 emission per square meter versus number of stories and building types. Now the embodied carbon of the structure is indicated in the black circle that you can see here, or there. So there's one building that has more than 160 stories. It could be Burj Khalifa. It has structural embodied carbon around 1,600 kilograms CO2 per square meter. And this is our CL Tower at 965 kilograms per square meter. So by looking into the graph, I would say we need a lot more data to be plotted in order to confirm if there is a clear relationship between the carbon footprint and the number of story in the tower. I would like to show you a proposed structural carbon rating scheme by well-known Mike Cook. It was also published on the Structural Engineer issue of October 2020. It is based on the estimated modules A1 to A5, cradle to practical completion of the primary structures. So the average carbon footprint is set at around 350 kilograms CO2 per square meters in October 2020. And the solid curves represents the global average target going to zero in 2050. And there's also an upper bound and lower bound for 40% better than average and 40% worse than average. So in order to achieve carbon neutrality by 2050, which is the challenge, we need to target a reduction of minimum 5% a year, because you could realize that the curve is relatively flat at the end. So I think the majority of the reduction had to happen now, but not later. So we can look into our design. We should provide design which have minimum impact. It can be done through a combination of lean design, efficient use of materials, and harness latest technology to make the concrete and steel greener. So for conclusions, I would say CL Tower is a challenging project for both design and construction. The architectural vision is well achieved. The design team has overcome various challenges, successfully deliver an iconic super tall tower, utilizing existing board piles. The structural engineer has demonstrated a significant role in an integrated design team. The structural solution is safe, efficient, economical, and finally, at NOR, we do care about sustainability. This is my last slide. So these are the 10 tallest hotels in the world by 2023. You could notice 7 of them in Dubai. Noise, very proud to have designed two of them. The Emirates Towers Hotel in 1995 and the Seattle Tower 2020. So this is the end of my presentation. Thank you very much, and we just go straight into the Q&A session.
Thank you very much, Turk. This was great. The presentation was great, and the work is outstanding. The actual design. Yeah, I'm not sure that we have a lot of time, but we need to just open this for some questions. Maybe we'll take 5 minutes of questions. I have just one comment. The photo on the from the air to show the foundation, it's as if everything was meticulous. You know, that you have or the contractor had arranged everything just to take the photo, and this is not a photoshopped clean site photo. Was it always that tidy and clean?
No, it's not, because you remember the site is just beside the Kayan Tower, right? Kayan Tower is also a 300-meter tall tower designed by
I know. I worked on that.
So, yeah, so somebody had climbed up there and then took the photo. Yes, it's a real photo. Yes.
Yeah. So, any questions?
So this is Marwan. That was an impressive presentation. Good to be in the picture as whatever happens in your part of the world, and Noor Dubai, of course, is close to us. Will continue to be so. On the graphs that you showed for sustainability, I think the number of story, if it is combined, that parameter, if it is combined with the area of the floor area, and the thing is normalized, we can get maybe a better curve or line. But I think the number of story means many things. It can be in a narrow building with a small footprint, or a wide building with a you know, the same number of stories. So each one will be different. But again, there is a grouping for low-rise building that is obvious. So the behavior for low-rise is probably mobilization affects it, because you mobilize for a small building or a tall building, all the same. Anyway, great presentation, and thanks. We'll look forward to the next one.
Yeah, thanks, Marwan. I do think that you know, for tall buildings, there's a lack of data being published, you know, so I think we're gonna need to some more time together, enough sufficient data in order to evaluate whether, you know, what is the right carbon footprint for tall buildings or super tall buildings. And of course, this number will vary based on, you know, from one geographical area to the other. So yeah.
Very good. So
yeah, just one quick one for the these panoramic elevators, the steel structure, the vertical steel structure. I take it that this was vertically isolated from the concrete because of the differential movement between the steel and the concrete.
Yeah. So this frame basically. What we have designed is that this frame laterally is restrained at the garden floors.
Right.
So basically, it's a horizontal structure spanning around in this case 27.5 meters, and then at the connection between the steel frame and concrete beams, we basically provide vertical slotted holes. So yeah, the gravity loads are all going down to the foundation levels.
Yeah. Good. Yeah. Excellent. Well, thank you very much once more. This was fantastic, and we thoroughly enjoyed it. And look forward to more of Noor Dubai with the Noor Canada interaction.
Sure.
Okay.
Yeah. Thank you very much,
All
everyone,
the best.
and
All the best.
join you
Thank
in the
you.
next workshop then.